Get ready for it. We're looking at Lesson 9, Efficiency. Please open your booklets to page 58. In this lesson, we really bring it all together. So the first law of thermodynamics, energy can't be created or destroyed, only converted from one form to another. So if we look at this beautiful world, we could say solar energy is converted to chemical energy in our little plants that we learned about. Think back to that, which is converted to chemical energy, which is converted to mechanical energy, which is converted to potential energy. So look at this, it all just came together, boom. We're talking total energy, the whole cycle here. So now let's look at the second law of thermodynamics. So no conversion of energy is ever 100%. And by that we just mean some energy will always be lost as useless energy in these conversions. So an example would be an incandescent light bulb might be said to have about 15% efficiency when converting electrical potential energy into useful light energy. So the rest of that energy is converted into thermal and sometimes sound or mechanical energy. So what we're saying is that light bulb gets hot. So some of that energy, instead of being turned into light, which is what we want it for, is lost as useless energy going into heat or even into sound. Sometimes you hear that like zzz. That's what we're talking about there. So it's not super efficient. It's not 100% efficient. And that's what this lesson is about. How can we calculate that percentage of efficiency? Well, I'll tell you how. So let's jump to the top of page 59 and let's look at an equation. One last equation for your book here. Okay, so we're going to say the percent of efficiency is equal to output energy divided by input energy times 100. And that makes that gives us a little efficiency percentage. So copy this down in your book. Okay. So let's look at an example, because page 59, examples are how I get my head wrapped around this stuff. So Jeff puts 200 joules of work into raising a book high up, so it has a potential energy of 150 joules. How efficient was this conversion? All right, well, let's go visit our old friend Grasp. Okay, so what's given here? We'd say the input energy, Jeff put 200 joules of power in there. Okay, the output energy, we're talking about 150 joules. Okay, right, because that's its potential. Okay, so what's required? Well, how efficient was this conversion? So we're talking about that. So let's analyze. We have our equation, we just plop it down there. Now all we're gonna do is plug in these numbers. So we're saying 150 joules divided by 200 joules, because that output energy, that potential energy of the book after Jeff lifted it up, was 150 joules, but it took Jeff 200 joules to get it there. So we just multiply that by 100, so it's not a fraction anymore, and we're gonna be blammo, 75%. We're just gonna paraphrase as usual. It took Jeff used 200 joules of energy to lift a book up, and the book stores 150 joules of potential energy, so the efficiency of the conversion is 75%. Pause here and copy that down. Moving on. Okay, one more for us. Now this one, wow, this is an exciting question. Not only because it has little toy cars in it, but because it brings together so much of our learning, and we really need to dive in here to get this. So, a kid's playing with a Hot Wheels set. Those are those little metal cars. The Hot Wheels car has a mass of 0.05 kgs and starts out on the track at a height of 76 meters. So it's like a little track, and then it'll use gravity to drive the car down the track, is essentially how this works. When the car is released, it reaches a maximum speed of 2.3 meters per second. So it's asking us, calculate the percent efficiency of the energy conversion. How much energy was lost as thermal and mechanical energy? So it's asking us kind of for two things here. We have to calculate the percent efficiency, and we have to figure out how much energy was lost. Okay, so let's get started. Old friend Grasp, can you help us out here, please? Boom, there it is. So let's just dig right in. So what's given? We know that this car has a mass of 0.050 kgs. The height is 0.76 meters. and the final velocity is 2.3 meters per second. And we also know, it's not written down, but we know that gravity is 9.81 meters per second. Okay, so what's this asking of us? So we're gonna start with percent efficiency. Percent efficiency. Now let's analyze. Okay, so we have written down what's there. We know what we need, so let's analyze this. Boom, our fancy new equation. Okay, now for this, we're actually gonna have to figure out a couple things. So how are we gonna start here? So I guess first we wanna think about what is our output? What's actually happening here? And the output is when that car is pushed down the ramp, what it actually does. And potential would be when it's just sitting at the top there. So when we break this down, that's what it is. So what we have to do here is we have to figure out that output energy, and we have to figure out that input energy and then plug it into this. So we have a few steps to this equation. So first of all, number A, let's figure out the kinetic energy of that car at the maximum speed. Okay, how do we do that? We have our old friend, kinetic energy equals half of mv squared. Okay, we can rock that. Let's just plug those numbers in. Boom, plug them in. And we come to an answer of kinetic energy is 0.13225 joules. Now we don't round it yet because we're not done with this equation. We will consider sig digs at the end, but not yet. We're just gonna keep it here so it's as efficient as possible. Okay, so what else do we need? We have output energy. What do we need now? You guessed it, B. Input energy is what we're gonna find. So that potential energy of the car at the top of the track. And again, potential energy, we look back at our old equation, mg delta h, or mgh. So with this, again, we just plug it in. Boop. Quick calculator fingers, and boom. We have that potential energy, or that input energy, of 0.37278 joules. We're not going to round it yet. We're gonna keep going though. We're gonna plug this in. So next step, we just did B. Now, let's look at the questions here. So calculate the percent efficiency of the energy conversion, and then we have to say how much energy was lost as thermal and mechanical energy. Okay, so let's start with that first little blue part. Calculate the percent efficiency of the energy conversion. So we have our equation, and we just plug it in again. So we decided that EK divided by EP times 100% would give us efficiency. So we're saying our kinetic energy when that car is at its maximum speed, divided by its potential energy when it was sitting at the top there waiting to blast off. And we just plug in the numbers, and blammo, we have 35%. That is beautiful. Okay, first question answered. Okay, now how do we figure out what is lost? How much energy was lost? And that's actually just a simple subtraction. We're just gonna say energy lost equals the input minus the output. Just like that. And we'll just plug some numbers into there because we have both those numbers that we already figured out. And we'll find that 0.24 joules is the amount of energy that was lost. So that was an amazing question. I'm so excited, and I think it's unbelievable that we can be figuring this stuff out. Like, imagine all the connections being made in our brains right now as we're figuring this out. Like, we are learning how to learn, we are learning how the world works, we are pushing this forward, and we have the opportunity right now to practice these skills together when maybe at other times in life we won't have the time to build these skills. Or maybe we'll have a whole host of vocations in life where we do. In any case, learning is beautiful, knowledge is power. Let's push this forward. Let's push our brains to do amazing things. We'll end it by paraphrasing it. As always, if a Hot Wheels car with a mass of 0.050 kgs is released from a height of 0.76 meters and reaches a speed of 2.3 meters per second, there will have been a 35% efficiency of energy conversion, and 0.24 joules of energy is lost. So that's that useless energy, which, you know, probably in the friction of the wheels on the track as it went down, as well as just the car itself not being that smooth a ride, etc., etc. So that's how much energy we'd lose it. I invite you to pause right now, copy this down, make sure you understand it, and then rock and roll. Let me actually go back a couple screens and let you copy down the other parts. So again, we started with grasp. Now we're going to identify what we see. 0.05 kg car, height of 0.76 meters, and a final velocity of 2.3 meters per second. And we figured out that gravity, 9.81 meters per second squared. And finally, we realized we're looking for this percent efficiency, which we know the equation for that. And we know that that's what we have to answer. But because of that, we realize we have to figure out what the output energy is and what the input energy is. So we're going to bring back previous knowledge here. And we are going to start by saying, okay, the output's equal to the kinetic energy of the car at maximum speed. And then finally, we know that EK equals half of mv squared. So we plug some numbers into that and we come up with these guys. Pause here if you need to. Otherwise, boom. We know now that we need the input, which we're going to say is the potential energy at the top of the track. EP equals mgh. And then we just plug those numbers in that we already have. So pause here if you need to. And now we're going to bring it all together to our big equation, and we're just going to plug those numbers in. So we know EK over EP times 100% will give us what we want, and we'll put these numbers in here and finally come to 35%. Again, pause if you need to. And we're going to say that in response to energy lost, we'll just say energy input minus energy output will give us those joules lost, which works out to 0.24. So pause here if you need. Copy this down on page 59 so you can reflect on it if you need to, or if you'd like to. And now, I think, again, what I really want us to remember is this is a huge question that brings in all kinds of information. The practice assignment works to bring all our information together, but it does it in a way that's structured. So we'll start with a little bit of easier questions and we'll work our way up. We'll build that knowledge as we work through the practice questions. So even if you're walking away from these examples we did together, you're likely walking away being like, wow, I have no idea what just happened. Or maybe you do have an idea and then you're ahead of the crowd, and that's cool too. But work through the questions and it'll start to make sense as you go on. Okay, so please complete the practice assignment on page 59 to 60 and rock and roll. Good luck. Party on. You can do this. We did it. Wow.